All right, thank you very much. Okay, I see a lot of people standing there. I think there are still a few seats over there. If some of you could probably squeeze in over there. All right. Okay, so I'm guessing by now you've heard a lot about Delta Lake and stuff since the morning, the keynote and talks after that. Some of you actually attended, I can see faces, some of you actually attended the workshop that we did in the morning with hands-on tutorial on Delta Lake. So here I'm going to switch gears a little bit and focus more about Delta Lake and how to make it, or how to design architect pipelines using structure streaming and that. So the focus is going to be on structure streaming. So I'm going to give a brief intro on structure streaming, but if you're not really familiar with how structure streaming works, you can learn more about it from my previous Spark Summit talks. They're all available on the Databricks website, where I go much deeper into how structure streaming works and how to write code using structure streaming. Okay, so in this talk, well, before I continue further, let me actually give a broader introduction of myself. So I was in AmpLab, UC Berkeley, where Spark was originally written. I actually started my grad school life by writing Spark streaming originally, and then slowly transitioned, which was around 2011, 2012. And since then, I've transitioned into writing structure streaming as part of Databricks. I'm a software engineer at Databricks right now, and part of this team called Stream Team, where our motto is, actually our original motto was, we make all your streams come true. And well, that's where it started. And then we realized that to make all your streams come true, we have to really solve non-streaming problems like making data storage and efficient. And that's why the Stream Team took up the responsibility of building Delta Lake to solve all the data storage related problems that you have heard enough about today since the morning. So for the uninitiated, Spark structure streaming is basically a distributed stream processing platform, which boasts a very high throughput, second scale latencies, and it's obviously fault tolerant, end-to-end exactly once guarantees despite any kind of failure, and obviously a great set of connectors in the ecosystem to read and write from various different data sources. And the core philosophy of structure streaming is to treat data, both batch and streaming data, as tables. So streams are nothing but essentially unbounded tables. And you as a user or developer write code using tables, like batch-like queries on tables, and it's the Spark structure streaming engine's job to take your batch-like query and run it continuously and incrementally on streaming data as new data comes into the system. So this is what it roughly looks like. Let's say you want to write a pretty common ETL pipeline where you're reading data from Kafka. This data is in a pretty complex nested JSON format. You want to really parse the JSON format into a proper schema and store it in a more structured data format like Parquet. Now, as a Parquet table and stuff. Now, and you obviously want end-to-end failure guarantees to ensure that none of your data is lost or duplicated. The code that you would have to write is something, that's it. Basically what you see on the screen. And roughly this code can be broken down into 4 clear parts. 1, you specify where to read the data from. 2, you specify how do you transform the data now that you have read it. 3 is how do you want to write the data, where do you want to write the data. And 4, when you're writing and processing, the details of how to exactly write and process. Do we want to do it in 1-minute micro batches or 10-second micro batches and stuff? So, and once you run this code and start the streaming query, what the Spark does underneath is takes your DataFrame code or SQL query plan and converts it to a logical plan, which is a very logical abstract representation of what is it that you want to do with the data. Then Spark's Catalyst Optimizer kicks in and does an amazing job of optimizing this logical plan into a far more optimized logical plan, just like a batch query would go through, but that's where the similarity with the batch query ends. In a batch query, an optimized logical plan translates to a single physical plan, whereas in structure streaming, the engine understands that this is a streaming optimized logical plan and therefore generates a whole series of incremental execution plans that will incrementally operate on the data as new batches of data comes in, incrementally operating on it and updating the results and writing out the updated results to the sink. So, and this all happens automatically. You just write a standard SQL query or DataFrame query, thinking of it as just a table. So that's structure streaming. Then let's talk about Delta Lake, which we have already talked about enough just to cover the basics. It's an open source storage layer that brings ACID transactions to Apache Spark. You get very good batch and streaming support. It allows you to do to mix batch and streaming workloads, in fact, concurrent workloads with all the transactional guarantees, schema evolution, schema enforcement, history, etc. We have hopefully have seen enough of this in today that you don't need any more information on this from this talk. But I think one key thing to remember, I think a different way that I think about it is, and not many other people may not think about it this way, but I think about it is that it essentially combines the best of both worlds of databases and data lakes. So databases are known for transactional guarantees, clean data, but not really known for their scale-out capabilities, whereas data lakes are known for their scale-out capabilities, not so much for their data consistent stuff. So Delta Lake, the point of Delta Lakes is to get the best of both worlds. Anyways, let me jump into the meat of this talk. So how do we build streaming data pipelines using these two amazing tools? Now, this question can be framed in a different way, which is what are the design patterns to correctly architect streaming data pipelines? Now, the way to think about design patterns is that there has been a lot of talk given in the past about streaming design patterns or using other systems and stuff. So why is this talk, what is the selling point of this talk? Am I just going to repeat the same design patterns that other talks have given? Now, the difference is that most streaming design pattern talks talk about one way of solving a problem because they are built on a pure streaming engine like Apache Storm, for those who have remembered Apache Storm from the early days of streaming big data. So they had only one way of solving a particular problem, whereas Spark, being a unified batch and streaming engine, there may be multiple ways of solving the same problem with different trade-off between cost and resource usage and performance. So it's important to understand in detail how to reason about what is the right way to do things given a particular problem. So this talk is going to talk about I'm going to talk about what is the right philosophy of thinking about design, what are the common design patterns, and in the future, beyond the Delta Lake and structure streaming that you have seen today, how are we going to make things easier for you to express your data pipelines in? Let's jump in. So for streaming pipeline design, let's start from the absolute basics. There are data streams, and what you want out of them in the end are insights. And the real challenge is what is there in the middle to go from left to right. So what I'm going to propose in this talk is think it in terms of these three questions: what, why, and how. So what stands for what is your input and what is your output. So what is your data that you're getting in? Is it from Kafka, JSON, Parquet, files, Kinesis, different sources possible? What is the format and what system is your data in? And what is your output? Where do you want the output to go to? What is that system? What sort of performance do you need? What sort of throughput and latency do you need? Now, and here the second question is why. And this is probably the most important question where people kind of, a lot of times I see people making mistakes. Why? You understand what you want, but why do you really want it? Who is going to consume the data? Is it going to be consumed by automated processes, or is a human going to consume the data by querying the data? And so how and when are they going to consume this? So here are common mistakes that I've often seen working with different customers. So people come and say that I want to build a dashboard which is with aggregated counts or something which is updated every second. My question is, why? Who's going to use the dashboard? Is a human going to look at it? Is he going to take action every second? nobody does that, right? There isn't a guy who's always staring at dashboards all the time, screaming, oh, something happened. So what's the point of updating it every second? Why do you want to overcommit your resources for just to achieve that? Second pattern I've seen, that I want to generate automatic alerts on aggregated values and stuff. Okay, not a dashboard, but automatic alerts. But the fine print is that most of my data is very delayed over hours and stuff. So then that begs the question, does it make sense to generate alerts within seconds or milliseconds if the quality of your aggregation is low because your data is mostly delayed? So does it make sense to generate the alerts at that low latency? Third is that I want to train machine learning models over the data that I've collected through my ETL pipeline, but somehow someone decided that the data is in a key value store, which some cases it is okay, but if you're training machine learning models, most machine learning models train by scanning over the entire data, which key value stores are not great for scanning over multiple data. So that is probably not the best design for building machine learning models at the end. So you have to think what platform you're using. Anyways, I can go on and on such mistakes. But let me move forward. And to the third and the last question is how to process the data and how to store the results. And my conjecture is that if you really understand what and why deeply enough, your how will automatically figure itself out. And that's what this talk is about, is to understand the streaming design patterns in the context of this what and why, and the how would automatically be figured out. Okay, let's jump into pattern. I'm going to discuss 5 high-level patterns in this talk, and hopefully that should cover a lot of the use cases that I've seen across different customers and stuff. So pattern 1, the most common pattern is ETL. I already took example of that, reading from Kafka and writing it out as a Parquet table, or let me generalize, as a structured tabular data. Now, there are, again, different, and why do you want to do that? Because someone, either a machine automated process or some humans are going to interactively query the tabular data for further analysis, be analysts, etc. So now, a common way of doing it is what I saw, what I spoke about is running a structured streaming on Kafka. But here, the kind of latencies you would get is minutes, or let me flip it. If you want latency a few minutes, then the best way to do it is use structured streaming, that is continuously processing the data, reading from Kafka or whatever streaming source, running 24/7 on a cluster and writing it out as a tabular file format like Parquet or even better Delta. Now, the advantage of Delta out here over other file formats is that you get all the advantages of consistency guarantees, snapshot guarantees when you're reading and querying the table while the table is being written. You can concurrently run other kinds of operations, like you can update the table to fix corrupted data. You can delete GDPR deletes and stuff like that while data is being written out and while other both humans as well as periodic jobs are doing queries on the table. So that's the advantage of Delta. But if you don't have a requirement for a latency of minutes, but instead you are okay with hours, then you can do something much cheaper. You do not have to have your cluster up 24/7. Rather, what you can do is that you can still use structured streaming, express all your code in structured streaming, but instead of running structured streaming query for 24/7, you run structured streaming query in this mode called trigger once. What it does is that you start the query in trigger once mode. It will run one batch, just one batch of to process all the data it has, all the new data it can see since the last time it ran, and then shut down automatically. So that means that it becomes like a periodic batch job that you can start. It will run one batch and stop. So then instead of structured streaming controlling the micro batching, you can schedule the structured streaming query, explicitly start it for one batch at a time from outside, like using something like Apache Airflow or a cron job, or in Databricks jobs. You can say that every hour, run this structured streaming query in trigger once mode. It will process all the data it has received since last hour and shut down automatically. And so And this can be much cheaper. If you don't care about minute scale latencies, if you're okay with hours, this is much better. And then on the flip side, if you want even lower latency, where you want to query up to the last second data, in some cases you can actually query the source directly. For example, for Kafka, you can run batch jobs using Spark directly on Kafka. So you can just run your batch queries directly on Kafka, and it will just read data up to the last second in Kafka and give back results. So third way of doing interactive queries on structured data from ETL jobs. Second pattern is when you have key value output. And this can happen when, let's say, you're doing continuous streaming aggregates. You ultimately want a table which has aggregate information. That can be either for simple data statistics over your data, or it can be sessionization, complex aggregates, etc. Now, typically there are two ways people would like to consume these aggregates, and that's the why here. Either the aggregates may be consumed by for lookup, like let's say a website wants to look up one aggregate at a time, or it can be used for reporting, like give me all the aggregates right now as a giant scan. So depending on that, the solution would be different. So let's say you want the aggregates to be looked up by a website one at a time. So for that, Delta is not the best solution. The best solution is to store it in a key value store, which are optimized for single key lookups, like Redis, Cassandra, name any one of them. And so you have to write your streaming query such that you write it out to key value stores, and the latencies you would expect is seconds and minutes. But on the other hand, if you want latencies not seconds but minutes, and you'd rather not do single point lookups, you rather want aggregates as an entire table for reporting and stuff, summary tables and stuff, then best to write it out into Delta Lake. And now Delta Lake supports this operation called merge, which is exactly like the SQL command merge, but we have both Python, Scala, Java APIs for expressing merge programmatically. But using that, you can combine structure streaming and merge together using this operation called for each batch. So what it basically does is that you can say, in this streaming query, compute the updated aggregates, and for each batch of output, take the updated values and upsert it into the Delta table using this merge operation. So that totally works, and actually, it's actually amazing how well it works for a large number of use cases where you don't need point lookups, or you don't need very low latencies and stuff. Okay, and what you get out of it is there are some complications are there when you're dealing with aggregates. You have to deal with late data, watermarks and stuff. So sometimes what happens is that to do this sort of stateful aggregation, you have to specify a watermark to limit the amount of late data to consider. I won't go into the details, but the bottom line is that sometimes you need to take a call on dropping very late data so that to optimize the streaming query process in order to keep the latencies low and stuff. Now, that does lead to some inaccuracies that you must be aware of. The other problem that can happen, but if you really want to not have any of those inaccuracies, you want to compute aggregates over all the data, then you have to do a trade-off. You have to say that you are going to dump, instead of computing aggregates continuously in your streaming query, you dump all the data just like a standard ETL job into a Delta table, and then do periodic aggregations on top of the final Delta table to create the summary table. So, and you have to accept latencies of hours, at least hours, if not at least hours, but you cannot do seconds and minutes. So there you can, with that you can ensure that no data is dropped even if it is late and stuff, and the answers are correct. So it all depends on what your data is and what is your business requirements, and you can do different trade-offs based on that. Third pattern, and this is pretty important in a lot of complex use cases, is that joining multiple inputs. So you have related data coming from two different sources, and they have a common key between them, and you need to combine them together into a single table. So there are two there are two ways of thinking about this. The multiple inputs can be thought of either joining a fast data stream with a slow data stream or fast stream with fast stream. A typical case of joining fast stream with a slow data stream is having a fast facts table and joining with a slow dimension table. For example, you have sales data coming in from point of sales devices and stuff. So these are product sale information that is happening millions per hour and stuff like that. But you want to join it with the product information based on the product ID to capture, to enrich the sales information with additional metadata. So that's an example of fast and slow. The way to do it is that write one ETL pipeline for the slow data to take the dimension data which changes much slowly. Have that as a slow ETL pipeline that is run periodically or continuously depending on the requirements. That writes to a dimension table. Have another pipeline that takes the fast data, higher volume data, and does a stream static join on the dimension table. So that means that you're joining, you're treating the dimension table like a static table because it changes very slowly in that fast ETL pipeline. So ultimately you get a combined table. And the cool thing is that there are, well, both the drawbacks with doing it without Delta is that structured streaming, once it starts a query with a static view of the table, it can never be updated. So you may have to, so if you want to make sure that the structured streaming query on the fast data joining with the slow static view of the table picks up changes of the static table, you have to restart the streaming query. And that leads to complication. And that is because structured streaming does not have the metadata to know when the slow table is updating. It just doesn't know. And that's where a better solution to use Delta, where because in Delta you have the metadata and the semantics to know when a table got updated. So structured streaming doing stream static join on a Delta table can automatically reload the table whenever there is any change on the table. And this is an optimization that is present right now only in Databricks, but we are working hard to push it out into the open source as well. But yeah, some of the advantages of Delta Lake, of how to think of it. But there are, again, in some cases, there are still drawbacks. One is there are delays in updating the dimension table can cause problems. Like for example, let's say you get a product sales information from a point of sales device even before the dimension table has been updated about that product. It's a new product, dimension table has been updated. So what do? Your join just doesn't find anything to join with. You are left with left outer join and nulls and all that stuff. In that case, treat it as a joining between fast and fast data. And that's the next pattern here. Fast and fast data, a canonical example of that is add impressions and add clicks. Ads are being shown millions per second, and people are clicking probably less than millions per second. I don't click on ads very much. So, but both of them are generated at a very fast rate. And the key thing is that both of the data can be delayed compared to each other. So the click, because of how data is uploaded through browser or etc., the click may arrive before the impression data or vice versa. The impression data the impression data is supposed to arrive before click, but there can be delays either ways. So that's when you should use essentially structured streaming, stream join. It is supported out of the box. And what it does is that it automatically, so in that you can specify how delayed your data can be using watermarks. And based on that, structured streaming will automatically figure out how to buffer the left data and the right data, how long to buffer, etc., and make sure and try to join it as much as possible. And so if you have these sort of general scenarios where you do not know which one will be updated before, then stream join is the way to go. Again, I have a deep dive talk on these sort of stateful operations in the Spark Summit that really goes in detail of how to use stream joins. Please take a look. Anyways, the pattern 4 is change data capture. And this is pretty common in scenarios where people have a database for OLTP workloads, like transactional workloads, doing point update queries from a website or something from a service, and they want to do not overload the OLTP database. Rather, they want to run analytical workloads on the same data. So they want to take the change data stream from the OLTP table and replicate it to some place where they can run analytical queries. Again, the best way to do this is using Delta Lake, which supports merge. In fact, the standard SQL merge is limited to only updates and inserts, whereas we support a much more extended syntax of merge, which includes deletes, which includes multiple match statements, match clauses, etc. And using that, you can do arbitrary change data capture. So you get a series of inserts, updates, deletes, and you can apply them in the right order and stuff on using this merge. And you can do it, again, from a streaming query as well. So read the change data stream from, let's say, bin logs on MySQL and stuff, and apply it to a Delta Lake table, therefore replicating the OLTP to a OLAP table. Finally, my final pattern I'm going to talk about is writing to multiple outputs. Now, this is, again, common in different kind of scenarios. For example, people want to update both the raw logs. So you have a stream of logs coming in. You want to store all the raw logs, as well as update summaries on top of those raw logs, or in the case where they want to access the change log stream as well as the updated table based on the change log stream, or they want to have, they are computing summaries where they want it for both key value lookup as well as for analytical queries and reporting and stuff. So how to do that? Now, updating in standard, there can be done in two different ways. Either you can do it serial or parallel, or that's the way to think about it. Each has its own advantages and disadvantages. So in serial, basically you are doing the first computation, writing it to table 1, and then reading table 1 once again, and to compute the second computation in table 2. Now, whether this is cheap or expensive depends on what is the data that you're computing in table 1. If table 1 is essentially much larger volume than table 2, then you're writing and reading back the same thing multiple times. That's not the best. And end-to-end, there's a higher latency. On the other hand, parallel, the latency is lower, but you are reading the source data multiple times, which has its own disadvantage that if the source table is in some sort of a unstructured or semi-structured format that requires heavy-duty parsing, then you're doing that heavy-duty work twice in parallel, which is a waste of resources. So typical workloads look like some combination of these two. So, and there are, at a high level, two ways possible to combine serial and parallel together. One is figure out that what is the initial parsing or the expensive step, do that first, write it out to table 1, so that reading from table 1 is much cheaper and faster, and then from there you can fan out to multiple streaming queries reading parts of table 1 to the necessary parts of table 1 to compute other tables. And there, if you store it table 1 in the right format, like Parquet, Delta, etc., partition pruning and column pruning, all the columnar format advantages can make it significantly cheaper if you take care of doing the expensive step only once in the first. This is good for like doing an ETL of cleaning up the data, parsing it, and then doing multi-level summaries down as a second step, or you want to capture both the change log as well as the update table. You can change log becomes table 1, and then merging the change log into the update table becomes the second step. But yeah, you're still reading, writing table 1 multiple times, but it becomes much cheaper. Second approach is that you can run a single streaming query and use for each batch to update multiple locations. So let's say you're computing summaries and you want to write it both, upsert it to a Delta Lake table for analytical queries, as well as update a key value store for OLTP workloads. You can do that inside for each batch. It's the updated summaries you can write to key value store as well as to a Delta Lake. This is cheaper than doing the other approach, but you have to keep in mind that because for each batch you're doing essentially arbitrary operations, structure streaming doesn't know how to guarantee exactly once, end-to-end exactly once guarantee, so that's a trade-off you will have to make. Anyways, so using combination of the serial and parallel, a typical production pipeline looks something like this. And this is our own log pipeline using our streaming log. We run a service in the cloud, so we get logs and stuff. So it is divided into these bronze tables where we dump our raw unstructured data. Silver tables, we incrementally parse it to make it more structured, and finally gold tables for all the aggregates and stuff, for both streaming analytics as well as reporting. Now, we realized that over time, the right way to think about is not to think in terms of individual pipelines and optimize individual pipelines, but to think about the entire DAG. And this is essentially our future direction, that as developers, what we really care about is the end result, the streaming analytics at the end or the reporting as the end. And we want to be able to reason about the entire pipeline, the entire DAG of all the steps, reason about it and say whether we are getting the correct final result in our reports or not. And so what we're trying to build right now is a declarative way of specifying the entire DAG, not just individual hops, but the entire DAG, and as a complete data flow for, and so none of the APIs is final yet. We're going to open source it soon, but our hope is that declaratively we will be able to specify the query that in each hop, what is the query to compute that hop, what are the semantics of where it is writing, the location, the schema, etc., and then specify for each of the hop certain expectations that this date must be in this format, or this column cannot ever be null, or if something gets violated, what to do, whether to fail, whether to alert and keep the data somewhere else, or to quarantine the data and things like that. So we are working on this, and the hope is that once the user specifies declaratively this entire DAG, what we will be able to do is run unit tests across the entire DAG. Either you can plug in unit test, small amount of data for unit tests in the beginning and see what report comes out on the other side. You can take the same pipeline and take it further by running it with large amount of batch data using, let's say, last months of log, validate it, etc. And then take the same pipeline and run it on streaming data for real-time purposes. So you should be able to very easily deploy entire new versions of the DAG, upgrade the entire versions, or roll back the entire version of the DAG, including rolling back both the code as well as the data in the delta, in the intermediate delta tables. So you should be able to do all of that. So we're working on this. So stay tuned. Please try out Delta Lake as it is right now, and we have a lot more exciting things coming up. So again, stay tuned. Thank you.
Thank you, TD. We have time for a couple questions, so I'll run over a microphone. Got it.
Okay.
Since we talk about that multiple stream from Delta Lake, so how many streams supported? For example, like from Delta Lake, I can more than 30 streams I can read and write. So
there is no hard limit on how many streams can read it in parallel. It just boils down to the storage of how well that scales reading the same objects multiple times. If it's S3, then it just horizontally scales very much. So there isn't any hard limit. But if it's something like, well, not in case of Delta, but a different example is Amazon Kinesis. It has actually limits on rate limits on reads, where you cannot fan out very much. But Delta doesn't have anything like that.
Okay.
And it all depends on which storage you are using. HDFS, if you read multiple times, there can be hotspots and stuff. S3, not so much.
Okay, so my question is, since we use the structure streaming, it's applicable for the per instance, right? So
Sorry?
the structure streaming when you use, it's like a per instance, we can use a read stream, write stream. Is there any limit?
There is no limit. There is no hard limit on that. It just boils down to performance of the storage layer.
Okay. So another question I have, like since we talk about the latency of minutes, okay, so not latency of seconds, milliseconds, when the Delta Lake not usable. So when you go for some time arbitrary sync, for example, like for storage, the sync as Azure Cosmos DB as a MongoDB API. In our use case, like we are able to achieve thousands of millions of messages per second till Delta Lake. Okay, from Delta Lake to Cosmos DB, not able to achieve because we don't have connectors. We need to write. So in this case, how do we proceed? So.
Okay, so that sounds a pretty complex question. So let me break down the question into one is latency of structure streaming with Delta, right? So structure streaming, let me be very clear. Structure streaming provides up to a few seconds of latencies at best, not lower than that, not milliseconds. So now if you use structure streaming to write to Delta, or for that matter, any file format, then expect something, the lowest latencies as tens of seconds in large volumes, minutes. That is because just writing to files has its overheads. So now, in your case, the second part of the problem is you're trying to write to both Delta as well as Cosmos DB. So there, I think something like a pattern of where you write using for each batch, you write to Delta and Cosmos DB within the same batch. That may work, but again, you lose exactly one's guarantee. If you want that, then you probably have to do it in a more serial manner, write to Delta Lake, and then have a separate downstream pipeline that reads from Delta Lake and writes to Cosmos DB. Okay, let's talk offline. I think it's important to understand the details of the what and the why to really figure out what is the how. That's how I think, really. Yes, well, okay.
Sorry, two quick questions. When do we expect these declarative pipelines? Do we expect in version 6 of runtime? And the second question, should be possible to use continuous, instead of microbatch processing, continuous processing with deltas in the future? Or like you said, the latency is too big to writing files, and that will not be possible.
Good question. So first one is, when is this declarative pipeline available? So we are planning sometime this quarter or next quarter to have a private preview available as in open source and this thing. So we don't have a concrete thing, but expect something by next quarter. So Q1. And second question was continuous processing, which is basically structure streaming has this experimental mode that can actually get millisecond level latencies, but that kind of naturally does not work with Delta, because after all, Delta is based on files. You cannot really open and close files at the rate of milliseconds. So it's fundamentally not compatible with that. Not fundamentally, not implementation, even just architecturally not dependent on that. So yes, I don't think there is any plans for that at all.
I think we have time for one more question.
Okay, thanks. Thanks a lot for your presentation, first of all. I have a question about the pattern number 2 you showed us, about key value output for lookup and analytics. In which case you recommend to switch from delta to key values and false? Like, I mean, what's the border between choosing pattern number 2.1 or 2.2?
Simply, what is the downstream workload? Is it doing, do you want to do key value single key lookups? Then not Delta, key value stores. If you don't want to do key value lookups, only large scans on the table, interactive jobs and stuff, then Delta. That's a simple way to think about it.
Thanks. Thank you very much, TD.
Thank you very much. You're an awesome audience.